Hello everyone, welcome to lecture 21 on finite element method. Again, we start with our roadmap and you will see this roadmap again and again. This was what we did at the beginning of the one-dimensional FEM. We also talked about different approximations that are inherent to a finite element scheme or a finite element analysis. And also we had a more elaborate version of that map in 1D. If you want to wrap up this 1D in a short presentation, it's basically this. It starts from a strong form. You multiply that by a test function. You use this sort of separation of variables if you want, and you integrate that over the domain. So if you just think of these steps, this is like step 1, this is a step 2, then the integration is a step 3. You will see that these steps exactly will also repeat now when we talk about two-dimensional FEM today. And after some steps, you can write that integral in terms of your shape functions to connect it to basically your approximate form. Now you get to this form, and then basically you can recognize your stiffness structure. Now, when we do that, you see that stiffness is a function of x. So the next step is to transfer these ends from the physical coordinates to the natural coordinate system. And then we did that using basically the transformation from x to c and integrating instead of the whole domain L over the domain -1 to 1. And once you have this form, you can transfer it to a summation over the Gauss points. This is exactly what we are going to do today, also when we have a two-dimensional finite element analysis. So now that we want to jump to this two-dimensional FEM, again, the roadmap is exactly the same thing as we did before, except that now in this form, we learned first how to do these approximations and shape functions. So we learned them last time, and now we want to go back to this part of the game. For that, we need some mathematical preliminaries. We talked about this. Again, I am repeating this because we are going to need all of it today. So we had this Einstein summation convention, then we defined dot product, double dot product, and dyadic, and also we had this thing we called Kronecker delta. And then we also showed that the relationship between stress strain can be written using a double contraction like this, in which now your E is a fourth order tensor, or let's say fourth order array for you. And also based on what we have learned just using this more advanced mathematics, we can now define gradient operator and divergence operator for vectorial fields or for tensorial fields. And if you do that, then gradient of a scalar field, it would be a vector. It's like that. The gradient of a vector, it would be a matrix. Then the divergence of a vector, it would be a scalar. And finally, the divergence of a matrix or a tensor, it would be a vector. If we collect all of this here, this is all you need basically, and these operators will be useful for what we want to do today. And we also mentioned that in view of what we do, a mechanical problem and a thermal problem are formally identical. It's just we are using different quantities. So we focus on the mechanical problem today, but later in your homework 6, there is this homework that easily shows you basically how you can also calculate the response of a thermal problem. Now, the strong form for a two-dimensional or a three-dimensional problem, in this case 3D, it's basically very simple. It's divergence of stress plus body force density is 0. For a mechanical problem, for a thermal problem is divergence of Q. Q is heat flux plus, again, some sort of internal heat sources densities if you want it to be 0, 2. In 2D, these relations, they will look like this. And as I mentioned, usually we assume this body force density or the internal source doesn't exist. Okay, so these are very important, and we will see all of them in today's lecture. Again, with respect to a mechanical problem, basically. We also come to this relationship sigma c double contraction epsilon. And when we talk about 2D, we should distinguish between plane strain and plane stress, basically. We will come to that too, but just think about it that we usually talk about plane strain here. It's just the change of the variables. Everything remains the same, but inside C, maybe you need to be more careful about your material parameters. Their meanings would change a little if you go from plane strain to stress. Then we talked about approximations, and we said, well, now if you want to approximate something in a two-dimensional space on a surface, it's exactly what we did for a 1D. So you need to draw the shape functions, and then basically once you have these shape functions, if you just write this formula in IFI, then you get the approximate f, or you get f as a function of xi and eta, which would be also its approximation. Then we talked about different approximation. In particular, we have 5 different elements here. 3 of them are square type or quadrilateral, and 2 of them are triangular. This one is a linear or bilinear quadrilateral element. Then we had Lagrange biquadratic quadrilateral element. We had serendipity biquadratic quadrilateral element. We had constant strain triangle, CST, and we had quadratic triangle. And then we also learned how to do the integration using the Gauss points in 2D. So we have learned all these little pieces that we needed to do a two-dimensional finite element method, and I will just bring back the roadmap that we had. So again, if you look at this, we had just learned how to do this. Okay, so what I want to do now is to go back here. We do this supposedly in the first hour, and the second hour I can kind of come to the second part of these two. Okay, so we will cover a big part of this roadmap in today's lecture. What we want to do is to formulate the finite element method in 2D. Okay, so basically what we want to do is to go from a strong form to weak form, and then later we want to go from, let's say, weak form to approximate form. So this would be the first one, from strong form to weak form. Now, I hope you remember the steps that I mentioned for a one-dimensional analysis. What we do here is very similar in nature to that. So except that now, instead of a 1D element, which was usually like a truss element, you have a body, okay? So a body is a two-dimensional body. Let's say this is your body, and it could be fixed somewhere. So let's say it is fixed here. Then it could have this, let's say, a free part of the boundary, or it could also have some forces or tractions applied to it. So let's say these are the tractions, and you can see here this is fixed. Okay. Now, if you want to identify or define the boundary of the body, you can say the boundary from, let's say, here to here, so all of it before you reach the fixed part, this is a Neumann type of boundary. Okay, so let's call this boundary of the body, but then we put this n here to stand as Neumann. Okay, so the whole thing together is just the body, let's say. Now that part would be the Neumann part, and then you have this part where you have prescribed displacement. So this green part, it would be the Dirichlet part of the boundary. Okay. And then again, remember, Dirichlet basically means you have prescribed displacements. So this is how a Dirichlet boundary condition is defined. Again, now this prescribed displacement, it could be zero or it could be non-zero. If it is zero, it's homogeneous. If it is non-zero, it's non-homogeneous. All right, so it's a prescribed value. It could be fixed where it is, or it could just move like 5 centimeters. You define what it is. Now, the Neumann type, on the other hand, it means that the tractions are prescribed, and then the tractions are related to the stresses inside the body using the Cauchy theorem, basically. So this, if you remember, we had this Cauchy tetrahedron, and you can write the balance of forces on that, and you can see that the tractions on the surfaces of that tetrahedron are related to stresses like this. And now, again, remember this T0, it means prescribed traction. And the unit of that is like force per area, basically. So it's Newton per meter squared. And this would be prescribed displacement. Okay, the unit of that is meter, obviously. But the important thing is, again, to pay attention that prescribed traction could be zero or non-zero. In this example, for instance, here, it seems that they are non-zero. So this is non-homogeneous Neumann part of the boundary condition, of the boundary, sorry. And then in these parts, you see here, there is no traction. So no traction means it's traction zero, okay? So these are homogeneous part of the Neumann part of the boundary, okay? So let me just maybe give you a more tangible example. Just think of a little square. Okay, imagine this square is now fixed here using our usual supports that you had learned also before in other courses. So you have this kind of supports on this side. And then on the other side, let's put this sort of support. So I am going to put rollers here like that. Okay, this indicates that, for instance, on the right-hand side, the points, the nodes, they cannot move in the vertical direction, but they can move in the horizontal direction, right? So something like these, so these supports, because they are completely fixed, these are in both X and Y direction. They correspond to being Dirichlet type. Sorry. All right. So what I'm trying to say is that being Dirichlet or Neumann, in this picture, I draw it as if it is dependent on each point or on each node. It's not like that. It is about a point and also about a direction. You can have Dirichlet in one direction and Neumann in the other direction for the same point or for the same node. And now that's exactly the case here. So if you think of this one now, in the x direction or in the y direction, it has two different types of behavior. In the x direction, it can move freely, so it's a Neumann. In the y direction, on the other hand, it's a Dirichlet, and it's a homogeneous Dirichlet in this case. Okay. Now let's make this a little more interesting. So if you apply also tractions here, so I'm going to apply non-zero tractions here. Then you can clearly see this thing, which we just called, it was Neumann, it's even non-homogeneous Neumann. On the other hand, if you look at a point here, this has no particular constraints in any direction. So this is completely Neumann. Okay, so what I'm trying to say is that you cannot just say this edge is Neumann or this edge is Dirichlet. This is wrong. You cannot exactly identify that for the whole edge. You should define it per point, per direction. That's how it's going to work for you. Okay, and then if you just think of this example that we have here, you should actually think about it. If you apply this loading that I just showed, let's say it was a square like this at the beginning, what will happen after you apply the deformation to this is that this thing is going to deform, and it's going to deform like this. Does that make sense? Because again, it's fixed here, it cannot move. On the right hand side, you are pulling it, but you don't allow it to move in the vertical direction. So this is what is going to happen to it. Okay. And it's a very nice example, and in a week or so you should be able to run it in the code that you have implemented. Okay, so I think it's a nice point to start with. All right, anyway, the important thing, or the thing I wanted to talk about here is that you should be careful about these boundary conditions. Again, they are formally identical to what we did in 1D in the sense that you talk about Neumann boundary condition, Dirichlet boundary condition, but you should also pay attention to these details because now you have two directions. You need to be careful about what happens to those two directions separately, okay? All right, so that's that. Now we go back to the strong form and we see how we can calculate the weak form out of that. So the strong form would be divergence of sigma is 0. And then I am just assuming that the body forces do not enter to the problem, that body force density is fairly trivial to introduce it to the problem. You can always do it at the end, basically, at the element level. We don't want to bring it to the discussion here, it's easy. So, and this is true for every point inside the body. Okay, and that body is subject to, so this is like a differential equation as we had before. So this is a differential equation, it's a second order differential equation within the domain B, and it's subject to boundary conditions at Dirichlet and Neumann types of the boundary. So it's subject to boundary condition, which is U equals U0 or sigma n equals to T0 again, this would be at Dirichlet parts of the boundary, and this would be at Neumann parts of the boundary. Okay, so this is what you have, what you're dealing with. And as I said, this thing is nothing but strong form. In the absence of body forces. Or body force density. All right, so what was the next step, or the first step we did? We multiply the strong form by the test function. Okay, so now we do exactly that. You multiply that by test function. So that test function is, again, the same thing that we had before. W dot divergence of sigma is 0. W is a vector now. And this is exactly following the properties of the test function that we had before. Remember, it was arbitrary, so this thing should hold for any W. And also W at Dirichlet parts of the boundary must be 0. All right. Now, the product in between is a dot product. So you have a vector, dot product, a vector. This is a scalar value. So this 0 is a scalar 0. Whereas the 0 you had here, this was a bold 0. This was a 0 vector. All right, so you have this. Let me just clean it up a little. Bring this up. But remember, W is satisfying these properties. So this would be your step 2. Now, what was the next thing? Remember, you had this sort of separation of variables, or integration by part, basically, but this is now in its differential form. So this thing, W divergence sigma, it's divergence of W dot sigma let me take these boundary conditions to the corner to save space. Minus gradient of W. So gradient of W is altogether a matrix now, because W is a vector, double contraction sigma. Okay, so I'm not going to prove this. This is an identity, but it shouldn't be too difficult for you to see where this identity is coming from. Remember what we had in 1D? In 1D, divergence of sigma was something like U double prime. So in 1D, you had W, so U double prime, and you wrote it as W U prime prime minus W prime U prime. Remember that? This is exactly the same thing. So this term is basically that. This U double prime was our strong form there. So now our strong form is divergence of sigma equals 0. W is the same W. Now, instead of this derivative, it's basically the divergence. Okay, and then this part, it gets a little more crowded because you are dealing with these vectors and tensors. But if you just think of the dimensions, I think this should be very clear for you because, for instance, you think of this, it would be a scalar value, so W dot sigma, it's a vector. Divergence of that is also a scalar. Gradient of W, that's a tensor, or that's a matrix, let's say, that's a second order tensor. Sigma is a second order tensor, so the operator in between must be double contraction. So basically that's how it works for you. This is the equivalent of that relation in 1D. Okay, and now all you have to do is to insert this into the previous equation and integrate over that, or over the domain. Okay, so that's what I'm going to do. So basically, if you insert this into our equation, you would see this equals this. Okay, and then you can integrate over the domain. So I'm going to do that. So I integrate over the domain B, gradient W, altogether double contraction sigma dV. Well, I'm writing dV if it was volume, but it's area, so let us just write dA. Okay, but and again, this means like the integral over the whole surface, or if it had a thickness, then thickness should be multiplied by that and it should look like a volume, but then that thickness would also cancel out from left and right eventually. All right, so that would be then B. Actually, maybe for clarity, let me just write it dV for now. That would be divergence of W sigma dV. Okay, but as I mentioned, let's think about this problem. It's a 2D problem. So what we think of a 2D problem is always like this, as if you have a domain and it has a thickness which is constant everywhere. Okay, so this is like a plane strain assumption, right? So it cannot change in that direction. So basically your dV would be T dA, and that T will cancel out from left and right. Okay, so from now on we will deal with only dA from that perspective. So all right, so if we do that, then we get this integral now. So this is our integral form. Let me also change these dVs to dAs. All right, so while we are at it, I just want to remind you of what we did again in 1D so that you can connect the dots in between. See what we did in 1D? We had a strong form. You multiply by test function W. You had also the discussion on boundary conditions. Then you had this exactly the same relation that we did here. We integrated over the domain. So these steps are the same. Now, what we want to do is to do the integral, or remember, one of the integrals we could just calculate based on the boundary values. Now we want to do the same thing, except that now for that, we need a theorem. We need this so-called divergence theorem. So there is this theorem called the divergence theorem. I hope some of you can remember it. it basically tells you if you have an integral of divergence of something, anything, over, let's say, that area, equal, that should be equal integral over the boundary of that area, that thing times n. That's the normal unit normal vector to the boundary of the domain. Okay, so this would be unit outward normal vector to boundary. So if you want to sort of draw it in this picture, it would look like this. Let's say here, this would be n. Here, this would be n. So it has the same dimension. So it's almost, if I draw it well, it's always outward, it's always unit vector. So it's like that. So basically, this divergence theorem tells you that flux of something over the boundary is related to its change inside the domain, which makes perfect sense kind of from a physical perspective. But and the reason I'm explaining it is that, as you can see here, you have a term which looks like that. So we have divergence of something over the domain. Now we want to connect it to its value over the boundary, and that's what we are going to do in the next step. So that's exactly what we will have now. So instead of the second term, I'm going to write its corresponding version using the divergence theorem. So it's going to be integral over body gradient W. The left-hand side is not changing. The right-hand side would be now integral over the boundary, and then that thing would be W dot sigma, and then dot, well, let me just do it without bracket because this is dot product. You can only interpret it one way. So that's that. Now, remember, the boundary is composed of Dirichlet part and Neumann part. So the boundary of the domain is the Dirichlet part of the boundary, let's say its union with the Neumann part of the boundary. By the way, the intersection of Neumann and Dirichlet type of the boundaries is obviously 0, or is empty set, right? So these two types of the boundary, they cannot coincide, but you have two portions of the boundary, and that's what I want to do. So the integral on the right-hand side, I want to just split it into two integrals. Okay, so we can just do that. I would duplicate this. You have that over the Dirichlet part of the boundary and over the Neumann type of the boundary. Okay, so now if you think of the first one, the Dirichlet part of the boundary, what can we say about that? Remember, in the Dirichlet part of the boundary, W is 0. So remember, the test function had these properties that, first of all, it's arbitrary, and second, we said W at the Dirichlet part of the boundary was 0. So you would do exactly the same thing. You can clearly see that this integral, the first integral, must vanish. Well, because this goes to 0, the first integral altogether should go to 0. Okay, so that's the first integral. Now, the second integral, it's only on the Neumann part. But see what you have on the Neumann part. In the Neumann part, you know sigma n is T0. It's exactly your prescribed fractions. So it's not an unknown to the problem either. Okay, so this is a very important step, because you come from having an unknown property on the right hand side to something which is completely known now. Okay, so basically what happens is that the right hand side term would change to just t here. So you would have wt0 dl. Okay, and that would be again on the Neumann part of the boundary. Does that make sense? So basically what we have done now is something very similar to what we had done again in 1D, and now we proceed according to the similar procedure. What we want to do next is to redefine these, or let's say carefully define what W and sigma are. So remember, we were using approximations to replace these functions, okay? So that's what we want to do now. Let me just take it down a little. So this is our first outcome. This is the first thing we wanted to do. Okay, so we wanted to have a weak form from a strong form. There you go. This is your weak form. All right. This is our weak form, and what we want to do now is to go from that weak form to approximate form. So we just did this part. What we want to do is now to go to this approximate form. How did we do that approximation? We did that approximation using shape functions, right? So now you need to introduce your shape functions into this game. Okay, so I'm going to use this as our, let's say, starting point now, the rectangle that we have. And maybe I even, well, yeah. So now we want to go from weak form to approximate form. And this is the weak form we have. All right, so what do? We introduce the shape functions. We introduce the shape functions first for W and then for U. You do not see the U here because it is hidden within sigma, within the stress itself. So if I have this W and I want to replace it using shape functions, remember W is Nj Wj. Okay, so Wj would be the W at point J or at node J, and Nj is the shape functions of that. And then J is basically your counter. And it's repeated twice, so it means a summation. So it's N1W1 plus N2W2 plus N2W3 and so on. All right, so if you do that, that means that gradient of W so gradient of W would be Wj diode gradient of N. All right. Okay, so you use that W on the left-hand side. So basically here, you know that gradient W is simply Wj diode gradient Nj. So this is basically a matrix or a second order tensor, as you can see from its definition. Now, this was about W. Let's look at sigma. I mean, T0 is given, so we don't have a problem with that. Let's see what sigma is. So stress sigma is related to strain via the relation sigma equals E double contraction epsilon. And E was a fourth order tensor. Now, if you remember, epsilon is the symmetric gradient of U. Okay, but because this E, it has its own symmetry properties. So it has its own symmetry. It has, by the way, two important symmetries. It's major and minor symmetric. But because E has that symmetry, you can simply say sigma equals E double contraction gradient of U. Okay, so you do not need that symmetry anymore because you already get that symmetry through the properties of E. All right, so what I'm trying to say is that you have a gradient W, so you see you get a form like this, but also you have a gradient U, which now you can clearly imagine gradient U would look very similar to gradient W. Okay, so that's what we want to do next. Remember, we said we approximate U and W according to the same approximation. So this was our sort of Bubnov-Kyorkin view on finite element method. So this thing is basically that. I have here sigma equals E double contraction gradient U. Now, again, as I said, we play the same game with U and W. So you assume that U itself is approximated using the same shape functions. Now I am using I as a counter so that we don't confuse it with J, but these are dummy indices again. So the I is repeated twice, it means it's a summation over that. So this is N1U1 plus N2U2 plus N3U3. So it's again N1U1 plus N2U2 and so on. Okay. And the same way, I mean, previously when we wrote that thing for W, this means it is N1W1 plus N2W2 and so on. All right, so if you have that, then you can just say then gradient of U would be UI dyadic gradient Ni, which is not too surprising. It's exactly the same thing as you had for W, but now you have it with I's. All right, so this is where we are, and now what we want to do is to again put that back to this equation. So instead of E double contraction gradient U, you can just say it's E double contraction UI dyadic gradient Ni. All right, so let's write that. So sigma is E double contraction UI dyadic gradient Ni. Okay, we have everything that we need to proceed. But just before doing that, just look at this. You have E in between. You have UI dyadic gradient Ni on the right-hand side of it. On the left-hand side of it, you actually have Wj dyadic gradient Nj. You can already see the nice symmetry in this example or in this problem. We will continue with that after a break. So I have 9:23. Let's have a 10-minute break. We continue at 9:33 sharp. All right, so we have come to this form now. What we want to do, as I mentioned, is to proceed with this, to simplify this, and then see how we can further elaborate on the form that we have to see the stiffness nature in it, like we did in 1D. So to do that, let me just clean up this a little. And maybe I shift this to the corner to make space. Okay. So this is exactly what we want to do. We have all the ingredients that we want to put into this equation, and I want you to actually see how we do it. All right. So now you have sigma clearly in terms of U, and you have the gradient of W. So if I just expand the form there, we go to the next step. But before doing that, I want to I want to just do one little simplification for our own notation. So instead of gradient of something, remember this, what is gradient here? Gradient is the derivative with respect to x, okay? Just to have a shorter notation, I want to just write it like this. Okay, so the derivative of that thing with respect to x, okay? This helps us in two ways. First of all, it gives us a shorter notation, but more importantly, this helps us to distinguish between the gradients or the derivative with respect to x, and later when we have the derivative with respect to the natural coordinate, c. So this would be equivalent of what we had in previously as a prime. Okay, so previously we had n, I don't know, n prime, and we said n prime is n derivative of n with respect to x. This is basically equivalent to that. All right, so if I just do that, and I will not do anything apart from that, I will just write exactly the equation that we have up there. But now I will use these terms specifically. Okay. So we have an integral over b. Okay, I'm writing this equation basically. We have an integral over b. W J dyadic NJ X double contraction. Now you have E double contraction UI dyadic NIX dA. Okay, so all of this is basically your left-hand side integral, and your right-hand side integral is, okay, that's slightly less involved. That's boundary Bn, so Neumann part of the boundary, and then instead of W, you have Nj, Wj, and T0, which is your prescribed traction, and let's say dl. dl is the length increment, obviously, on the boundary. Okay, so what we want to do next is to play with this a little and see if we can simplify this. Okay, so we have this so far. Now, E is a fourth order tensor. What we want to do is to expand that E, the fourth order tensor that we have here. So E itself can be written like EA, B, C, D. EA dyadic, EB dyadic, EC dyadic, ED. Okay, so if you expand it like that, and then you look at what we have here on the, let's say within the integral, I'm just talking about the term within the integral itself. You basically have something which looks like this. You have, let's say you have a second order tensor, double contraction, a fourth order tensor, double contraction, another second order tensor. Okay, so this is second, this is second, and this is fourth. So what is going to happen between these is that you would have something like A, A, B, E, A, B, C, D, B, C, D. Okay, so if you just look at it, how basically it is constructed is not very complicated. You can see that the pair CD is contracted or is double contracted here, and pair AB is double contracted here. Okay, so basically A goes with A, B with B, C with C, and D with D. All right, so this is what you need to do. It's basically just a double contraction with a fourth order tensor. We had this before, but since now we have it from left and right, maybe you need to refresh your memory. But otherwise, it is not more complicated than what we had before. So remember, when we talked about fourth order tensor, we actually had this. Okay. All right. So this is what we are going to use next. We will basically write these in terms of their components. So this would be an integral over B. Then you have Wj, component A of that. Then you have Njx, it's a vector again, component B of that. Then you have E, A, B, C, D. And then you have Ui, component C of that, Nix, component D of that, dA, and then the right hand side is exactly what we had previously. But now also to make it more related to that, I will also write it like this. So this would be Wj, let's say component Q of that, and then this would be T0, I don't know, component Q of that. Right? So it's a dot product. If you remember the dot product, it works like this. So U dot V is U1, V1 plus U2, V2 plus U3, V3. It's exactly how it is on the right-hand side. All right, so now you have your approximate form. It's still not very familiar to you. Let me just. Okay, so what we want to do next is to further simplify this to make it even more familiar. So what can we do here? It's our usual integral, and we do exactly like we did in 1D. We take out the constants out of the integral. That's a typical step, right? So now what are the constants here? The constants are these. On the left-hand side, these are the constants. On the right-hand side, this is the constant. Okay, so you just take them out of the integral. And then again, it is exactly how we also did it when we had a one-dimensional version. Okay, so we take that Wj A out from left, then you have this integral over b. Then you have njx, it's b component, e, a, b, c, d. Then you have nix, it's d component, dA, and now you take also u out. Intentionally, I put u on the right-hand side to just remind you of something, but obviously it doesn't matter if you write it like that or not. And then this is then wjq boundary Neumann, and then you have nj t0 qdl. Okay, I hope I didn't miss anything. All right, so this is your approximate form, but maybe it's still not quite familiar, so you cannot yet recognize what's going to happen to this. So let's simplify it one step further. To do that, maybe we should analyze this. So let's see what this is. What are we talking about? These two indices, B and B, these are dummy, right? These are summation indices. The same holds for D and D here. Okay, so these are just dummy indices. Or again, summation indices, and they repeat twice, so that they mean a summation. So basically this thing, this whole integral, if I just look at it, if I just look at this integral altogether, how many free indices or how many free scripts, subscript or superscript, how many indicators does it have? That's the question basically. So B and D, these are not free, so they don't do anything. But here you can clearly see you have a J, an I, and then again an A here and a C here. So you have 4 scripts that are free. Okay, so you can change them. You can just say I is 1, I is 2, or I don't know, B or C is 1 or 2 or A or something. So they are free. So instead of all of this integral, I want to just call it something. Does that make sense? So that thing would have 2 superscripts, Ji, and it would have 2 subscripts, A and C. And I'm going to call that K. Okay, so if I tell you, or if I give you a specific J, I, A, and C, you can calculate this. This is a number, okay? If you know J, I, A, and C, you can calculate this, okay? That's the idea. There is no left unknown within this, okay? Now, maybe you have a good idea that J and I they are not in the same limit as A and C. So A and C are the coordinates, right? So they can be 1, 2, 3, sorry, not 3, 4. In 3D, they would go 3, but here we have 2D. So A and C, they are 1 or 2 basically. Whereas I and J, they go through nodes. Okay, so it depends how many nodes you have. They are related to the node numbers. Remember again? These are the shape functions, and shape functions were related to nodes, right? All right. You can also see it by this. So I is the node counter. Okay, so you can imagine this goes all the way to the maximum number of nodes, basically. All right. So if you now see this, then I can write this whole thing then based on what we just discussed. I can write the whole thing as follows. I can say it's W J A, then we have that thing K. Let me just write it without brackets. I think you understand what I'm saying now. So it would be K I J. So maybe I put the brackets here to see it better. And sorry, this was Ji, right? J is on the left. And right, it is Ji because J is here, I is here, J is on the left. So it's Ji A C, and then you have W I C. This would be, now on the right hand side, we have W J Q.
It is UIC, I think. UIC.
What's that?
The third term, UIC, you wrote WIC.
Oh, yes, thank you very much. Thank you. So it's UIC. So that would be WJQ on the right-hand side, and then you would have this, again, this integral boundary Bn Nj T0Q. Dn. All right, so we have this now. So we will proceed with this form. Now I just want to put this definition on the right-hand side or somewhere. Let's store it so that we don't forget. And maybe at this point I can remove this. So this definition is your stiffness that we are dealing with in the next equation. We don't yet recognize it, but it is actually the stiffness. So this would be your, what did we call this thing? KJI AC. Okay, so this term here is exactly that integral. All right, so we have now this. What can we do next? We have not used the properties of W. Remember we said W is arbitrary? And this is exactly the same game again that we kept doing when we dealt with 1D. So also when we were using 1D derivations, at this step, we had this one equation or one long equation, and then we said it looks like one equation, but because that W is arbitrary, you can set different W's and extract different equations. This is exactly the same thing we are going to do. So we want to use the arbitrariness properties of these W's, okay? let's do it exactly the same way that we did before. We can assume that, for instance, one of these W's or one of these W components is 1 and it is 0 elsewhere, or all the rest are 0. So first of all, think of it like this. WJA, again, this means at node J, this means in direction A. Okay, so direction A is basically X or Y if it is a two-dimensional problem, right? So let's think about this, for instance. Think of W11. So at node 1 in direction 1. Let's say that is 0. Sorry, that is 1. And all the rest are 0. So what does it mean? It means your W1, it is 1, 0. Again, it is 1 only in the first direction. So even W1 in the second direction is 0. Okay, so it is 0. And then all the other ones are anyway 0 completely in both directions. All right. And let's say we are talking about one element. If you think about only one element, these I's and J's, they would just run from 1 to node per element. Okay, so I and J, they would run from 1 to node per element. Okay, so if we do that, what happens here? What can we learn from this? So if you look at this one now, let's simplify this. Let's see what happens. So basically I'm saying if J is 1 and if A is 1, you get 1 here. Otherwise you get 0. Okay, so you can calculate all of this, but they would be multiplied by 0 if J and A are not 1. Okay, so that's the idea basically. So if you assume this, combination that W1 is 1 and then all the other W's are just 0, then what you will see is something like this. K one I, so J must be 1. If J is not 1, it's something which is multiplied by 0. Okay, that's the idea. And then A must be 1, C, U, I, C. You can see now for U actually it doesn't change anything. On the right hand side though, now you see the same story. If Q is not 1 and if J is not 1, then you just get 0. So J and Q, they should be both 1. So basically on the right hand side, you get this integral n1 T0 in the one direction, dA or dL in this case. Okay, so again, now looking at this is the traction in the one direction, in the first direction. Direction one is the x direction. Okay, you integrate that, well, or you integrate the weighted version of that because you multiply it by its shape function. You calculate that. So the right-hand side altogether, you can interpret this as F1. So this is force at node 1 in the x direction. Okay, and then again, x here is related to the 1. All right. So you may just call it F11 for now. Or maybe just to be more consistent, you can also write it like that. All right, so this brings us to our next slide. So it turns out that we can write, or we get to this thing, that this is now F1, 1. And as I said, this is like F at node 1 in the x direction. This was for this combination. So W11 was 1 and the rest was 0. So you can imagine if you play this game for all the other direction, you get similar results. Okay, but I'm going to, before I do that, I want to expand that a little. So let's see what we can learn further from this one. Let me just make some space. Okay, so let's expand this. If you wanted to expand this, what does this mean? This is K11 in one direction times U1 in the first direction plus K11 in the two direction times U1 in the second direction plus K12 in the first direction times U2 in the first direction. Do you see what I'm saying? So I is a summation and C is a summation index too. Okay, so you basically get these summations over I and C. So this thing means you have a summation over I and you have a summation over C on the left-hand side. And that thing is equal to your F1x. So if I write that, okay, if you write that in, let's say, further, what you will see is something which can be written again as all these components in a row matrix times particular components in the, let's say, a vertical matrix, a column matrix or an array, and that would be that your F1 in the one direction. Okay, so I want to just do that for you. So it's basically like this. It's K11 1 and then you have K11 1 2, then you have K12 1 1, K12, 1, 2. Then you have K13, 1, 1, K13, 1, 2. Let's say we have 3 nodes. Okay, so we can imagine that we have 3 nodes for simplicity, but you already get something which looks like this. And as I mentioned, we have 3 nodes. So what is a 3-noded element? It's a triangle. If it was a square, or if it was a quadrilateral element, so this is a linear triangle. This would be your K component, and this would be now your matrix. It's multiplied to. It would be U1, 1, U1, 2, U2, 1, U2, 2, U3, 1, and U3, 2. And all of this together is just F1, 1. Okay, so now if you think of these 3 nodes as nodes 1, 2, 3, so this is node 1, this one is node 2, and this one is, let's say, node 3. You clearly see what's going to happen. So basically, each node has 2 directions to move. So node 1 has directions 1 and 2, which means it's X and Y. Node 2 has directions 1 and 2, and node 3 has directions 1 and 2. Okay, so U11, it's corresponding to displacement of node 1 in direction 1. U12 is corresponding to the displacement of node 1 in direction 2. Then you have U21, that is the displacement of node 2 in direction 1, and so on. Okay. So just to make this a little more clear, I'm going to draw this with different colors. Okay, so these 6 directions, or let's say your displacement vector is, it has 6 rows, 1 column. Your stiffness row, it has 6 columns, 1 row. All of that is just the force of node 1 in the X direction. Okay. So how many of these do you think you have? So this is force of node 1 in direction 1, which is again X direction here. Okay, so this subscript is the direction, is X, superscript is a node number. So how many of these do you have? You have 6 of them. Each of them constructs basically 1 row of your stiffness matrix. Your displacement is always the same. And basically that's how this thing is going to work. So if I come back to this slide, and now we play the same game for a different component. So here, remember, we said the first component of W was 1. And the rest was 0. So in the next one, you can say the second component of W is 1, and the rest are 0. if you assume that, so let's play that. Now we say this is 0, this, you would say this is 0, this is 1. Now if you do that, you talk about still W1, so the J counter doesn't change, but the direction will change to 2 now. Okay, so this would be direction 2. Now, if you play the same game like we did here, let's do it. You play the same game, you would have a 2 here. But on your J, sorry, here, you can see that your J is still 1, your direction is 2. So if you look at all these you have here 1, 1, 1, 2, 1, 1, 1, 2, 1, 1, 1, 2. The first components that they were previously 1, they will be 2 now. Okay, so I'm going to just change them here, and I make them maybe red so that you see where the change happened. All right, so if you now think about this, we basically have 2 rows of this matrix. So let's write that matrix together based on what we have now. This was the second row, and we had the first row previously. So, and we are writing it for a linear triangular element, right? So you should remember that. So this is the second row of that matrix. Maybe I can put it here. And the first row of that matrix was this. Okay, let's just make them touch each other a little. I hope you can see what's happening here. So if you keep playing this game, you basically get a matrix that is 6 by 6, and it has this very nice structure, and we are going to just do that. So basically, each of these, so first of all, you would get a matrix that is 6 by 6. I think that is easy to see. But more importantly, I want you to see what is happening with these, let's say, blocks of the matrix. So if you think of this block all together, this is a block of K 1, 1, which is a 2 by 2 matrix. Okay, so this is a 2 by 2 matrix. Do you see? So this one has 1, 1 here, everywhere. Yeah, here. You see 1, 1, 1, 1, 1, 1, 1, 1. And then look at the components. 1, 1, 1, 2, 2, 1, 2, 2. So this is like x, 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 y, y, x, y, y. So you should think of it as K11 is basically a matrix. K11 is basically a matrix which is looking like this: K11XX, K11XY, K11YX, K11YY. Okay, which is not so surprising to you, because remember, if you had even a truss in 2D, you already saw this structure, that your stiffness for each component, it would have these four structures. I mean, in that example, you had like cosine squared of theta, and then I don't know, cosine sine theta here and there, and then it was like sine squared or something. So you had that matrix for each of these. So you have seen this before, that if you are talking about a two-dimensional problem, that nodal stiffness is no longer just one scalar value, is actually a 2x2 matrix by itself. Okay, so that shouldn't be too surprising for you. So basically, the idea here is the following. If I can go back to what we had, let's say here. Now we know how to handle this sort of problems, and we don't have to think of them as I and J and so on. So basically, you can say that if I have this, so we want to generalize this, not for any one anymore. So you can always say that if I have a J here, so if this was KJ and AC here, and then also on the F side, you would have, FJ, and in the direction A. Okay, so this is basically your system. Now, in this example, we no longer need to think of these W's, but the most important thing for you is to understand what this thing means. So KJI is the stiffness between nodes I and J. Okay, and it's a 2x2 matrix, or it's a 2x2 matrix block. Obviously, now if you have an element like a triangular element, and if it has 3 nodes, I and J, each of them could go from 1 to 3. So you would get 3x3 of these, and that would be your, let's say, your bigger matrix, the stiffness of the whole element. So I'm going to now clean this a little further. So let's say we are now dealing with this form. There is no W in it anymore. And I dare to also draw a rectangle around this. So this is our second rectangle of this lecture. And this is your approximate form. So the first one was the weak form. This is the approximate form. Eventually, so we introduced the shape functions and everything so far. But I want to elaborate a little bit more on that. So if you want to think of the components of this, let's see what the components mean in this. All right, we have really 1 minute, so I will talk more specifically about the components and the construction of this in the next lecture. But for now, just let's remember this, that Kij then, or sorry, Kji, it could be Ij, by the way, at this point, it doesn't matter. So Kji is just a matrix which looks like, again, in 2D, this would look like Kji 1, 1, Kji 1, 2, Kji 2, 1, Kji 2, 2. Okay, so that's that. Before we go further, I want to do just a notational simplification here. Don't get confused, but I think for some reason we like to see I and j in a reverse order. So here we have ji, ji, ji everywhere. Usually we are more familiar with ij. So these I and j's, they are just any number between 1 to number of nodes, right? So we can also change their orders. So that's what I'm going to do. So they are between 1 to 2 nodes per element. So if you have a 9-noded element, then okay, you have 9 of them. But what I'm trying to say is that you can just switch the order of I and j. And if you do it consistently, everything should be good. So this would be I, j. This would be then I. This would be j. Hopefully, if I didn't make a mistake with that. Oh, yes, I did. So this should be I. This should be j. Yeah, this kind of also makes more sense because now you clearly see that j is multiplied by j, so it has that nicer structure that reminds you of what you have done also in 1D. Again, this is just a notational preference, but I want you to see that from now on I will just write ij because it just keeps naturally more sense. Okay, so that's that. And the same here. And eventually this should be I and j in the reverse order. What was it again? Yeah. So this should be I, this should be j. All right, so this is usually the more common format. It's always written as I and j. All right. Thank you very much for your attention. So we pick it up where we leave it off today. So this is where we are. We know how to construct the stiffness for an element. What we need to do in the next lecture is to integrate this using the natural coordinates. And then again, before we go, I want to make this connection to 1D FEM. So if you remember in 1D FEM, we did exactly this, and we came to this point, and we saw that the stiffness was something like this. So we have this. This is done. What we need to do next is this step. So we need to go from physical space to natural space, and we need to talk about integration over the Gauss points. That is all that is left. Otherwise, we are in good shape. Thank you very much for your attention.